So the goal is to find the cube roots of -8. And what that means is, for example, z is supposed to be the cube root of -8. Z is to be determined. There's one answer that's easy, right? What is the cube root of -8? -2. Like you guys have been doing that for years. But it turns out there's actually several different cube roots of -8. How many are there? There are 3. Whatever that power is, that's how many answers you're going to have. So we know that -2 is one of the answers, but we want the others. So let's put the cubed on this side. So we're looking for solutions to that. Some number cubed is -8. And it turns out to solve this, we want to go to polar form, everything in polar form. So instead of z, I'm going to write some generic r e to the I theta that I don't know what they are yet. And this is the tricky part, is writing -8 in polar, which is weird because -8 is just a real number already. So what you can do is just, it's kind of silly, but plot -8. It's out here. Oh, yes, it is. -8. So the question is, what's the r and what's the theta? Well, the r is how far that point is from the origin. How much is r? So you could say r is -8. If I say how far, what would you say? You'd say +8. Turns out you could say either one. But if we say +8, then what angle are we talking about going from our standard positive x-axis to the point? It's pi, 180 or pi. So that means that theta is pi. So this is going to look a little different than what we had here, but it turns out there are a lot of equivalent and right answers. So I've plotted my point. I feel like it's walk 8 at an angle of pi. That's where -8 lives. Okay, so that means that instead of -8, we can put 8e to the I times what? Pi. Okay, and then we will cube everything. So what do we get on the left? R to the cubed, e to the 3 times I times theta, or 3 times theta times I. Just bring that 3 in. And that's supposed to equal 8e to the I pi. And now finally, I feel like I have simpler stuff that I can equate. What do you think r cubed is going to equal? R cubed, what do you think it's going to equal? Probably going to equal this 8. And let's see, I've got a 3 times a theta. What do you think that's going to equal? The pi. Right? You just make the things that are in the same places equal each other. So we'll write down 2 brand new equations. R cubed is 8, and 3 theta is pi. And so how much is r? How much is r? 2. Cube root of 8. And how much is theta? Pi over 3. So that's a perfectly good answer right there. R is 2, theta is pi over 3. I can write it as 2e to the I times pi over 3. That number right there is a cube root of -2. But we said there are how many cube roots? There are 3 of them. And the way to get the others is to recognize that when we said that the angle up there in purple in that picture, we said the angle was pi. Aren't there a lot of angles that say go straight to the left? One of them is pi. What's the next one? That says go straight left. What's another angle that says go pi plus 2 pi? Right? Or pi plus 4 pi. You could add as many 2 pi's as you want. And so maybe up here we'll say it could have been plus any multiple of 2 pi. They would all land straight to the left.
If you wrote it like that,
Mhm.
is that okay? Or would you specifically say, I want 5?
We want to see 3 answers. We definitely want to see 3 answers. Well, you could write that, or you could say, okay, we could have had pi, and just as well we could have had plus a 2 pi, and just as well we could have had plus a 2 pi. This is fine. Ultimately, that's what we need to get to. The 2 pi k is just like a general way to write it. So then dividing each of those new angles by the 3 to solve for theta. What's the next angle? That's pi. And the last angle, 5 pi over 3. That's dividing, basically that's 3 equations right there. Divide them all by 3. So that means that our other answers, it's still the same r every time, 2e to the I times, what's the next angle? Yeah, we got pi over 3 already, so that's now pi. And then finally the last one, 2e to the I times 5 pi over 3. So last thing about this one, I think really the hardest part here is to remember that you need to convert that number, the -8, into some polar thing. You got to get your hands on the polar form of stuff before you can do anything. Any questions on that one? That's a special case. The Euler's formula is e to the I theta equals cis theta. Yeah. The cosine theta plus I sine of theta. Yeah. So we'll start today on page 30, but first to look at the calendar, the updated calendar, which you'll find a copy of on the table. So make sure you grab one of those little slips of paper. That's the calendar for the rest of the semester where everything was pushed back a day. So that has the correct date of the test, for example. So that's a good thing to know. Everybody have one of those little scraps of paper for the new calendar? Okay, so today we're going to keep talking about vectors. We will finish vectors. If there's time, we'll start parametric equations. Tonight's homework is going to be about vectors. We're going to spend 2 days on this thing called parametric equations. Then we review for our test, and our test is now officially moved to May the 2nd. When is that? Yeah. What day of the week? When is it? Wednesday? Okay. So Wednesday, a week from this coming Wednesday, is our 3rd and final test. In between now and then, what do we have? We have a quiz on the 27th. When is that? That's Friday. Okay, Friday coming up is our 9th quiz. And then officially the project, I think, was due today, but you can hand it in Wednesday, and that's fine. So any questions about any of the stuff coming up? Okay. So on page 30, we're just going to refresh our memories about some of these things that we did here with vectors. So remember, a vector has 2 pieces. It has a length or a magnitude, and it has a direction, generally given as an angle away from our standard x-axis. And the nice thing about these vectors is that it was fairly easy to take them and break them up into their components, into their x piece and their y piece. So for example, that red vector right there, which was a 4 kilonewton force at an angle of 30 degrees above, we could figure out exactly how much of that 4 is pulling straight to the right and how much is pulling straight up. Do you feel like more of that 4 is pulling right or up? More is pulling to the right because that's a 30-degree angle. It's a pretty small angle. But if it were a 70-degree angle, then more of that 4 would be pulling up. So that 4 turns out to be broken up. You can see that we did the work over here using our favorite two formulas. X is r cosine of the angle, and y is r sine of the angle. And we figured out that that 4 has two pieces. The x piece, the right piece, is a force of 3.5, basically. And then the up part was a force of 2. It's okay that that sum is more than 4, right? We're not saying that the total then is a 5.46. It doesn't make sense to add those two things. One of them is straight to the right and one of them is straight up, and they honestly have nothing to do with each other. They don't even feel each other. So don't add them and think that we have now a total of 5 and somehow we've made 5.4 out of just a 4. They don't add up. But what does add up is if you have a second vector like the one in purple, and you break that into its x and y components, then what can we do? Which pieces can we mush together? Yeah, you can mush the x's together. So we figured out that the top x was 3.46 and the bottom x was 1.8. Those are both pulling straight to the right, so you can add them together. They work together. And we ended up with this 5.27 was the net result, pulling straight to the right, adding them up. And then the same thing, the y's go with the y's. There was a 2 straight up, there was a negative 0.5. That's because the second force was pulling downwards, and so they, in some sense, cancel. And just add them up, although it's a subtraction, and you get a smaller force, 1.15 positive, so it's up. Yes?
If you're doing the same thing in 3 dimensions, you do the same thing, you just isolate like the axis.
Yes, so you could have a z component as well, and you add the z's just as well. Okay, so it turns out there's a real convenient way to write down these components, these x pieces and these y pieces. So it's down here in number 7. So we'll get a reader for 7. Can we go to Chris? Okay, let's pause right there. So we now have two vectors that have just been given specific names. If you see the letter I, it's not imaginary in this case. It is now telling you go 1 unit to the right. So this little tiny vector right here is and shall ever forward be named y, 1 unit to the right. And what does j mean? It is 1 unit up. Okay, I is always, what's that? Why is that? We do have I. I don't know. Yeah, I mean, the context will make it clear. I mean, yeah, it'll make it clear. Also, technically, the like these, the I's and J's should be italicized, or maybe on top of it should be like a little arrow to say, hey, we're talking the vector known as J. Garrett mentioned 3-dimensional stuff. If we had another direction, a third direction, what letter do you think we use? It's K. So I, J, and K are the standard letters for the 3 directions. And so what does that mean? Well, take a look at this vector right here. This vector used to mean, whoopsies, this vector used to mean walk 2 units to the right and 3 units up, right? Okay, well, that's kind of wordy. Mathematicians like notation. So instead of saying walk 2 units to the right, what do you think we say? 2i. And instead of 3 up, 3j. And what symbol can we put in between? Plus. That's our compact way of saying walk 2 to the right and 3 up. 2i plus 3j is that vector right there. Yeah, that's the uncomfortable part, is that you're right. The imaginary axis was this vertical axis. It is when we're plotting imaginary numbers, but not right now. Now it's the j-axis. These are not the choices that I made. I'm as consistent internally as I can be, but this is standard. Well, so the question might say, yeah, it might have the arrow over it. Here's a question that we might have. Todd, read number 8. Okay, so this has nothing to do with imaginary numbers, right? Like this is movement, this is motion, this is vectors. So this context will be about vectors. If I said, you know, I've got something like 3e to the I times pi over 4, what do you think that I is? Do you think that's the vector I? No, that's our imaginary I. So there's context associated with it, all right? So I know that it's the same letter we use, but the context will make it clear. So instead of saying walk 2 miles east, what is that in terms of I and or j? To I. 2 miles east is just to I. Can you guys fill in the other 4 of those with your neighbors? Okay, so what is this part D? 2 east and 3 south? 2i and then minus 3j. Right, so south is negative j. Okay, and then 5 miles northwest. So first question was, is it perfectly northwest? And the answer is yeah. So which way is northwest? Up and left. So how do we represent going 5 in that direction? And what I'd like to do is figure out like how tall is that and how wide is that? That's what I want to know. So I claim that the numbers aren't obvious for like how long they're supposed to be, but we have work that we can do. That 5 is our R value, right? It's how far. Can you guys tell me the angle that will get us there perfectly northwest? Yeah, so we'll say it in our standard, always from the positive x-axis. And what you're looking for is the x piece and the y piece, and we have formulas. The formulas for the x and the y in terms of the r and the theta. What's our formula for x? R cosine of theta. That's what you're going to use. So we're doing 5 cosine 135 and 5 sine of 135. Todd, what do you have? Yes. Okay, so we type them in. Does it make sense that they're equal? Yeah. So it's perfectly northwest. Does it make sense that the x is a negative number? Yes, because we went which way? We went left. We went west. So that's a negative. Does it make sense that the j is a positive? Yeah, we went up. So as long as you use the correct angle, that 135, its standard position, the signs will take care of themselves. Okay. All right, so that's good. There's a little bit in the homework about the geometry of like adding angles up. Like, what does it mean in the picture if you have a vector? If you have a vector v, and you want to know where is the vector 2v. So I'll let you play around with that in the homework, and we can take questions before class next time. But I'd really like for you guys to have time to do this group activity about the swim. So let's get somebody to read, and then we'll set you guys up for a little bit on your own. We'll go to Vance. Okay, so we'll go to Kyle, number 1. Okay, so let's try this. So we've got the river going which way? Due south. Okay, so there's my river between those two borders. And I know that I am going 20 degrees north of due east. So carefully translate that into a picture. 20 north of due east. Yeah, so the x-axis, the y-axis, x is good. Yeah. Okay, so we'll draw a little horizontal there and then 20 degrees north of that. You guys buy it? 20 degrees north. And I'm swimming how fast? 0.7. So we're going to put a 0.7 as the length of that vector, the magnitude. And then what is the current doing? It's 0.3 which way? Straight south. So at the, remember the tail to head business? So at the end of my vector, you're going to put the current, which is always pushing me straight south. And you want to try to draw it roughly to scale. It's supposed to be a 0.3, which is maybe around half of the length of the vector we just drew. So we'll draw the current going straight south, about half. So possibly we're going perfectly sideways. That was kind of my goal with angling myself up, was to roughly go across the river. But we got some work to do to figure out exactly what my real path is. Is it perfectly to the right? Am I going to angle up a little bit? Maybe I'm still going like 5 degrees up, or maybe the current is such that it's actually still pushing me a little bit south. So let's put these pieces together and see if we can do some work here. We have a lot of practice with triangles, and we're going to make a triangle. And the last piece of the triangle is what the net result of my swim plus the current is. I'm starting over here. Where am I ending? At the bottom of that 0.3, right? Like that right there is the net result. Like I'm actually, that's what you will see if you watch me swimming. And I will appear to be going that way. I feel like I'm going up and then getting pushed down, but the net result is that red vector. So the goal is to figure out stuff about that red vector. And we have lots of information about the triangle so far. You have two side lengths, 0.7 and 0.3. Doesn't matter to me that those are velocities as opposed to lengths, just a triangle. So I'm going to treat them as lengths, 0.7 and 0.3. Is that enough information to tell me all about the triangle? A side and a side? If it was a right triangle, yeah, we need an angle. We need, or the other side, but there's no way for me to know at the moment how long the red thing is, the red side. But we need an angle, and that's not a right triangle in there, unfortunately. So we got to come up with some way to find an angle in that triangle. So you want to extend the 0.3, so we'll draw this down here. And yeah, we will. But yeah, it's not 0.3 anymore. But if we could find the something, then we could do some work, I think. But finding how much is left over is difficult. And Garrett claims that actually there's nothing left over, so maybe it's kind of misleading to draw that blue thing there at all. But maybe actually the red should have been drawn down there, in which case like I'm actually overshooting the right angle. Like it's really hard to know exactly what's happening. So here's what we're going to do. I'm going to go back to high school geometry. That 20-degree angle is useless at the moment because it's cut by the red line. And I don't know how it's cut. Cassidy? Mm-hmm. Let's pause. You guys remember some high school geometry?
No.
So back in high school, maybe you had this kind of a Z picture drawn in. And if you had parallel lines, then there were a lot of angles that were the same as each other and a lot of angles that added up to 180. And when you had this kind of Z drawn in, Cassidy mentioned the name of those two angles. Anybody else remember the name of the angles when you have a Z? Yeah, so exterior, interior, those were common words. Kelsey? the alternate interior angles. That's the 20 and the one that we've marked up here with that arc. And there's a nice theorem in geometry that says when you have alternate interior angles from parallel lines, what's true about them? They're the same. So that 20 gets copied right up there. And now we're ready to talk about an angle inside of our triangle. How much is left over for that green? That's a 70 in there. Right? Because it was due south, we know that there's a right angle on the other side of the purple, so there must be 90 on the left side of the purple as well. All right, so I'm going to draw that picture a little bit enlarged and then ask you guys to find some stuff about it. So we've got a 70-degree angle up here, a 0.7 here, and a 0.3 here. And what we're after is two pieces of information. I would like to know how long that side is right there. And I'd also like to know how much this angle is here. So can you guys try the law of sines, law of cosines, whatever you think is appropriate to find one and then the second of those two pieces of information.
So that's just without the current pressure balance.
Okay, so I'm just going to run through some of these answers here. On number 3, trying to resolve the original vector, my 0.7 at a 20-degree angle. We just use our r cosine theta and r sine of theta. And so we get the two components. What this really means is that I am trying to swim at a speed of 0.658 meters per second due east, just straight to the right, and a 0.239 meters per second due north, straight up, okay? That's what I'm attempting to do. The river is trying to push me at a 0.3 straight south. You don't have to do any work to find that, you just have to think about it. You don't need to use your r cosine and your r sine. Straight south is just a minus 0.3j. So are there questions on the green and the black vectors? Okay, and then again, the nice thing is if you have your components, your x's and y's, your i's and j's, you can just add them. That's how they work together. So we add them up, 0.658 I is unaffected. Why? Yeah, the river has no east-west motion at all. It's just pushing me south. So everything that I'm trying to do heading east is going to stay heading east. But the part that's going to get messed up is the part going, I'm trying to go north, and the river is pushing me south. And you can see here the river wins by a little bit. That negative 0.3 is going to counter my 0.239 up, and it's going to win. It's going to push me a little bit south, which is exactly what we got when we did the law of cosine stuff before. So anyway, this is my resultant vector. This is what it will appear that I am doing to somebody just watching me. And then down at the bottom, it says go back to the vector from number 1 and answer the component question. And just thinking about the vector from number 1, you got to be really careful. The vector from number 1 said that you turn out to be going at 0.661 meters per second. And what angle from our standard x-axis? It's a negative 5.26 degrees. It's not 25 degrees. It's not positive 5 degrees. It is a negative 5 degrees because sine and cosine assume the angle you give it is the one from the positive x-axis. And that's a negative, okay? So the r cosine theta formula, like it's a really, really great formula. It's a wonderful tool to use. Make sure that the theta you're plugging in is actually the theta in standard position. You have to take the angles that you're given and find the angle that's in standard position. Sine and cosine don't know. When you say 25 degrees, they have no idea that you're saying it's really 25 degrees from this random line that I was trying to swim on. Okay, it has no way of knowing that. Okay, and if you do this out, 0.661 cosine of negative 5.26, I can do that in my head. It's 0.658. Isn't that impressive? Just like that. You want to see me do the other one in my head? This is a negative 0.06. What? Allie can do it in her head too. Look at that, a human calculator. And then, oh my gosh, surprise, that is the same as that, right? Okay, we're going to move on. Any questions on this one? Any questions on this one? Okay, so let's, all right, so the homework is right there at the bottom of this page. We're going to move on to the next section, but that is the only homework that is assigned for tonight. And let's go to the next page, 33. Okay, can we go to Garrett for, can you read number 2, Garrett? On page 33, for example. Yes, please. Okay, so I'm telling you that there was like a car that traveled along this path, and all I can see is the dirt tracks that were left from the end of it, right? It was raining, and I could see in the mud exactly what path the car took. But I can't know, looking at just the tracks, whether it was going this way, or perhaps the car was actually going the other way, right? So all I see are the tracks, the leftovers. I also can't know, was it going at a constant speed, the whole time, or was it going really, really quick? And then it kind of took its time as it, like you have no way of knowing if you just look at the path, like the traces, the things that are left over. So in this section, we talk about this thing called parametric equations, which is a way to describe a path, but giving you more than just the, here's what it looked like when it was finished, but rather telling you exactly where it is at every moment in time. All right, so let's go back to number 1 for Hillary. Okay, so that's the weakness that we have with me just telling you the path of the car was y equals x squared, but you have no way of knowing where it was at any moment in time or how fast it was going or what its acceleration was, none of that. Vanessa for 3? Okay, so this is a new way to think about equations. It kind of looks like, what does it look like? A piecewise defined function? You guys know those, right? Where the different rules for the different inputs. Okay, it's not a piecewise defined function. I'm being very explicit. I'm telling you that time is the underlying variable. And if you know what time happens to be at this moment, you can plug into the equation at the top to find what the x coordinate is of the car, and you can plug the equation at the bottom for the y coordinate of the car. So for example, I could ask you, where is this car after 1 second? So we're going to plug in t equals 1 into both. How much is x? X is t, which is 1. How much is y when x is 1? It's also 1. It's 1 squared. So where is this car at the moment when the stopwatch says 1 second? It's at the point 1, 1, right there.
Isn't that the same as if we just label the x-axis?
Yes, this one is. Yeah. Now, how about where the car is at t equals 2 seconds? How much is the x? X is 2. How much is the y? It's 4. Right, plugging in 2 for both of the t's. So I can plot the point 24. It's right here. T equals 2. It's that point. Last one we'll do, 3 seconds. X is 3. Y is 9. So that's way up there. And so this, I'm hoping you see, is a much more informative way to talk about what this car was doing. Do you agree it's going to leave that track in the mud? It's going to follow that parabola. So we still get the remnants that we got before, but more than that, you can know exactly where this car is at any moment in time. You want to know where it is? You plug in the value of t, and you got your point. That tells you where the car is. And you can say more still. There's a certain distance that the car traveled in the first second. Then there's another distance the car traveled in the next second. Is it the same? No. What was the car doing? It was accelerating. The car was definitely going faster for that green part of the trip than the purple part. Because how much time did it have for both parts? It had 1 second. Going from t equals 1 to t equals 2. It had a second to travel the purple and then it had another second to travel the green. It must have been going faster when it was doing the green. Okay, and so you can talk about velocities, and you can talk about accelerations. You can talk about a lot of stuff if you just have this parametric version of the path. Okay. It says here, put an arrow on the parabola to indicate direction of travel. So I guess we can do that. Looks like the car is traveling that way, which, sort of thinking backwards in time, I guess it meant it was coming down the parabola on the other side. Okay, we'll go to Steve for 4.
Variable t is called
Okay, so the parameter is t. It is now the true independent variable. X depends on t. Y also depends on t. So for the first time, X is not independent anymore, right? X depends on something else. So t is this true underlying independent variable. It does its own thing. X and Y react. They're both functions of the t. We'll go to Garrett for 5.
Consider the parametric equations x equals t plus 1, y equals t divided by 2. For 0 is less than or equal to t plus than or equal to 5. I'd like to see what motion this represents.
Okay, so we'll go to Topher for A. 5A, yeah. Okay, so maybe we can make a table here. We've got t. The table's not on the next page, right? Is it? So I think we're going to make it up. Yeah. Okay, so let's make a table. We've got t, we've got x, we've got y. What values of t am I saying? So it's the integers between 0 and 5. So what's the first integer? 0. 1, 2, 3, 4, and 5. So let's go ahead and plug each of those 6 numbers into the x and the y. Once you're done, you're going to plot those 6 points on the next page. Oops. Okay, so we plot 6 points, and maybe one of them is in the hole, but that's okay. 2 of them are in the hole, and then
Business about solving one equation for t.
yeah, we're going to do that right now. So we get something that sure feels like it's linear. I didn't know it was going to be a line looking at those 2 equations. We don't have a lot of practice with looking at parametric equations. But anyway, it turns out it's a line. I would put an arrow to indicate direction of travel. This is a line going up and to the right. It could have been a line going the other way. Okay, we'll go to Kelsey for B. Okay, so we've got x equals, what was it, t plus 1? All right, so let's go ahead and solve that equation for t. Get t is x minus 1. And what was the other equation? T over 2. And what are we going to do? So we get y equals x minus 1 over 2. Yes? Any questions about solving for the t and then plugging into the other? Maybe writing this in standard form. 1/2 x minus 1/2. What is that the equation of? That's the equation of a line. Okay, now I'm not surprised that it looked like we were getting a line. What's the slope of this line? 1/2. Looking at the equation, all right, the graph seems to say the same thing. What's the y-intercept of the line? It says it's negative 1/2. Officially, we never get there, but if you did continue, you buy that we're heading towards this line, the y-intercept at negative 1/2. Okay, so what we just did is something called eliminate the parameter. What letter is the parameter? D. It has been eliminated. We have only x's and y's. We're back to a normal looking xy equation. So that's how we eliminate the parameter. All right, so now we'll go to part C. Allie?
That was
Okay, so you already know how to graph 1/2 x minus 1/2, but we don't really have a way to get the calculator to stop at t equals 1 or start there at x equals 1 and then stop at the end. So this is something new. And what I'd like you to do is go into mode and scroll down to that thing that says FUNC. Where do you think we're headed? Par, which is not a golf term, it is parametric. So hit enter, set it to parametric, then go into y equals, be surprised. Okay, looks different. All right, it says x1 with a t and then y1 with a t. Okay, super, I can type this in. What was x equal to? T plus 1. Where do you think we're going to find the t? It's on the x button. The button that says x also says t. T. Plus 1. That's the x equation. And then you hit enter and you go down to the y equation. T divided by 2. Those two things make how many graphs? They make a single graph. If you wanted to graph a different thing, you go down to x2 and y2. It's just like the y1, y2, y3, y4, but now they come in pairs. Allie. The t has to be specified. Different values of t give you different pieces of that line. So let's specify the t. Where do you think we're going to find the values of t? It's inside a window. Be surprised. What were our values of t? 0 up to 5, right? So let's go. No. Sorry. Yeah, we could here. You figure it out. It's a good question. Let's come back to that. Okay. All right. We were going to go up by, I mean, it doesn't matter what you go up by. I'll go up by 0.1s. That's just telling you how often it's going to put a dot. Oh, in fact, let's go by ones. Okay. We get the same line we had before. You ever seen a line just stop like that for no reason on your calculator? No, this is how you make it stop. What if you wanted it to go further? Yeah, extend that t. Maybe we'll go up to t equals 8. Maybe we'll start at t equals -3. And we get more of the line. You can get whichever piece of the line you want, but Allie points out, like, we need to know, like, t is not always positive. T can be anything. If it's time, it's probably a positive, but the values of t certainly affect the graph that we end up getting, okay? All right, that is good. Okay, let's go to 6. 6. We'll go to, where are we now? Steve in the back. Steve. Okay, so there's a whole slew of these guys here. Maybe we'll try one together and then first thing next class, we'll just do a bunch of them in your groups. How about we do, what can we do here? Let's do C. Let's try C together. Okay, first thing we're gonna do is make a table, just like before. What values of t do you want to pick here? Okay, so we'll go 0, 1, 2, 3, 4, and 5. Wonderful. Did you just put 1 there or no?
For what?
Instead of t over t?
Oh, probably.
No, not t over 1, but just 1.
For here?
Seems to me you just want this to be 1.
Right. T over t made it seem more like
Yeah. So maybe it's a parabola. Any other guesses? Like, I mean, it could be it feels, I mean, like there's t squareds in it, so it feels like parabolic. Any other thoughts? Okay, so maybe it's parabolic. So let's eliminate the parameter. That means solving either equation for t. I'll solve the first one. X minus 1 is t squared, right? Now, technically, we should solve for t. And what does that involve? Square rooting and plus or minuses. But let's not do that. The goal of this is to just substitute into the other equation. Can't you right now, instead of t squared, put something? Yeah, I mean, it's right there. That is t squared. So sure, solve for t, but really you just want to get rid of the parameter. Get rid of the t however you can. So it's okay to stop a little bit early. So what does this say? This says that y is equal to 2 times what? X minus 1. 2x minus 2. So that one's linear. Surprising, because we had t squareds in there. But somehow the t squareds ended up kind of like, they were, like the x was moving faster than normal because it was a t squared, but the y was also moving faster than normal because it was a t squared. And they both end up kind of canceling out. It's just oh, I see. So you didn't like me calling it a curve. Okay, so let's graph this thing on the calculator and then we'll call it a day. So we're going to type into the y equals x equals place. Okay, so we go back to the original. What do we have here? T squared plus 1. And then 2t squared. And I want to think about my window because I want to see the whole thing. I don't want it to shoot off the top of the screen. So let's think about the window. First of all, what t min is set up? It's supposed to be 0 by definition. T max? 5. What's the smallest x value you see? The smallest x value is 1. I'm going to go, I'll go like -2 just to make sure I can see it. What's the biggest x value? 26. I'll go to 30. I just want to see it. What's the smallest y? 0. I'll go -2. Biggest y? 50. I'll go 55. Then if we hit graph, we should see the line taking most of the window, but not quite all. Right? We can see the start, we can see the end. Okay, we'll do more of this next time. See you guys on Wednesday.